All right, so our next speaker is Jorge Sanchez, and he will talk about characterizing the oldest metal poor brown dwarfs as a key benchmark for exoplanet atmosphere comparison. Take away.
Can you all hear me? Ooh, nice. Let's just test if this works. Perfect. So good morning, everyone. My name is Jorge Sanchez. I am a fifth-year PhD candidate at Arizona State University. And I'd first like to thank the organizers of the Solar System in Context meeting for letting me talk to you all about brown dwarfs this morning. And I'd like to talk to you about, in particular, the title of this work is Characterizing the Search for Galactic Relics, Characterizing the Oldest Metal Poor Brown Dwarfs in JWST Deep Fields. Thanks. Ooh, lighting. So I'd first like to start off by giving a shout out to the PEARLS collaboration. PEARLS is a group of scientists working on studying extragalactic deep fields with JWST. And in particular, I want to give a shout out to those folks mentioned in blue here who have been really instrumental in seeing this work through. So since this is a solar system in context meeting, I thought I'd start off by showing the solar system's giant planets. And the trend we see here with the mass and metallicity for the giant planets of the solar system. And like good astronomers, we want to fill out this plot with observations of giant transiting planets seen with JWST in gray here, as well as planetary mass objects and brown dwarfs shown from direct imaging missions in blue. And so when we combine this information with constraints on carbon and oxygen, like on the right here, we can begin to predict the formation migration histories of these planetary mass objects. But sort of the region of this parameter space that I'm particularly interested in is on the bottom right here, where the most metal poor objects lie. And in particular, I'm interested in the physics and chemistry that govern these metal poor planetary atmospheres and how we can compare those to the more metal-rich objects we see in the solar system or in the exoplanet population. And so a recent example of a metal-poor planetary-like atmosphere was published recently by Faraday et al. 2025, where they found an extremely metal-poor brown dwarf dubbed the Accident. And with JWST spectra of this object, they identified water, methane, and in particular, this interesting silicon molecule, silene. And so the presence of this light silicon molecule hinted at this atmosphere being metal poor. And in fact, the results of their analysis concluded that this object had a metallicity of -2.2. Not only that, but the kinematics of this object suggested that it wasn't from around here. And instead, it was more consistent with the kinematics of halo stars. And so an origin in the galactic halo for a metal-poor brown dwarf makes sense, since we know that from stellar surveys at large distances from the sun, the population of stars that exist in the thick disk and halo tend to be part of this older metal-poor population of stars. And so since we know that brown dwarfs form similar to stars, there should also be a population of metal-poor old brown dwarfs at these distances. And so while we found metal-poor brown dwarfs and other planetary bodies that are metal-poor as sort of these interlopers that have been zipping by the solar system with these high kinematics, is there an opportunity to instead probe directly the population of brown dwarfs that we believe to be metal-poor in situ where the population of metal-poor stars exist? And so that's where JWST comes in. And so I want to talk to you about how using deep multiband imaging with JWST allows us to identify these metal-poor brown dwarf candidates deep in the thick disk and halo of the Milky Way. And in particular, as part of the extragalactic program PEARLS that I mentioned you before, JWST observed the North Ecliptic Pole time domain field. And this field was observed using 8 different NIRCam filters at a total area about 55 square arc minutes down to about a 5 sigma point source of 28.5. And so that entire field coverage of JWST is shown in these orange overlays here, these different spokes or epochs of observations. And if we zoom into one of these spokes, we can get a glimpse of the sort of remarkable images that of extragalactic objects like high redshift galaxies or AGN that PEARLS was originally designed to study. But I want to convince you now that deep in these images lie faint galactic brown dwarfs. And JWST and the amazing quality data that JWST can provide will help us tease out those objects. Here is one of those objects. So in black here, I'm showing our actual NIRCam data. And we fit this object, this source, with a suite of atmospheric brown dwarf models as well as extragalactic SED templates. And we found that it had a nice agreement with a T-type brown dwarf at about 1,500 parsecs and 1,100 Kelvin. But we also didn't just look for objects consistent with T-dwarf colors. We wanted to search for the most metal poor objects at even larger distances. So we also looked for L-dwarf objects. And here's an example of an L-dwarf candidate we found with an extremely metal poor atmosphere at a distance consistent with the Milky Way, the thick disk of the Milky Way, and possibly into the halo. And so in total, our search in the 55 square arc minutes of the NEP yielded about 41 new brown dwarf candidates, and 11 of those being consistent with metal poor objects less than 0. And so the search for these metal poor objects required new atmospheric models, not yet available in the community, that had metallicities extending down to the types of metallicities we expect for these metal poor halo or thick disk stars. So I also want to introduce a new extension of the low-Z model grid, which is a brown dwarf atmospheric model grid that already exists, but this sort of extension now brings the temperature range from 300 to 2400 Kelvin, as well as metallicities down to minus 3.5 dex. And so when we take our candidate objects, and what I'm showing here is the height above the disk as a function of our best fit metallicity, we see that the most metal poor brown dwarf candidates are consistent with thick disk scale heights and into the Milky Way halo, which is in line with the stellar population that I showed earlier. And so finally, and this is my favorite part of the talk, I want to actually place our solar system in context and show you how far we've been able to find brown dwarfs so far and where we're headed with JWST and these deep field surveys. So first, I'd like to orient ourselves with the sun here at 0, 0. And now we can plot our closest brown dwarf neighbor, lumen 16. So far, so good. And now let's plot the distance out to which all sky surveys like 2MASS or WISE could reliably detect a T-dwarf. So here's 2MASS at about 20 parsecs, and here's WISE. Then we can zoom a little further out and notice the scale change on the axes. And so now we're down to about 400 parsecs. The spheres start to shrink. But now, what if I change this scale from parsec to kiloparsec? Those spheres become little small dots. You can barely even see them anymore. So now what I'm going to do is I'm going to plot the T-dwarf candidates we found in the NEP. Here they are. Before I show that, I show the scale height of the thick and thin disk. And here are the NEP T-dwarf candidates that we found. I can also plot other candidate T-dwarfs found in other JWST surveys, like those gray stars right there. And finally, those L-dwarf candidates that I talked to you about, the most metal poor objects that we think are at the furthest distances, are all the way out here. So what we're really seeing is JWST's transformative ability to detect these most distant metal poor brown dwarfs out to distances that we have not been able to before, to study a population of brown dwarfs unique and not seen in our own solar neighborhood. So with that, I'll leave you with my summary slide, and I'm happy to take any questions. Thank you so much for your attention.
Great talk. Questions? The question there in the back.
Hi, Zachary Hartman, NASA Ames. So what are the errors on your distance estimates?
Yeah, that's a great question. So right now we're just doing a sort of chi-squared fitting, where we're just taking the best template that we find. And so we're incorporating things like photometric error, like the uncertainty from the actual photometry. And we're also trying to incorporate the error on the different model grids from the different distances we get from the different model grids, right? Because the different model grids that we tried also have different estimates on the distances themselves. Oh, those typically we've seen those are around 50 to 100 parsecs.
Cool. We do have time for a quick question. If somebody, okay, that's one day.
Hi, nice talk. I'm Sun Tang from Rice University. So I just want to ask, like, the super metal pool brown dwarf, what's the metallicity compared to our known stellar objects, the lowest metallicity stellar object, and also compared to like the planetary object we observe nowadays?
So the question was the comparison of some of the metal poor brown dwarfs to like the solar neighborhood.
The lowest metallicity in brown dwarf, right, compared to the stellar objects, and also compared to planetary exoplanet we know nowadays.
Right. So the candidates that we've been finding here are some of the more metal poor objects that we've seen in terms of brown dwarfs, especially within when you compare that to those like within 20 or 40 parsecs of the solar neighborhood. But these are also objects with just the photometry, and so we're calling them candidates so they don't have confirmed metallicities from their spectra yet. That's something we're interested in getting with cycle 5 observations. But in terms of how they compare, their metallicities are much more consistent with, like I mentioned, the population of the halo stars, where we don't see anything below sort of -1 within the solar neighborhood.
All right, with that, let's thank Jorge and all the speakers this morning.